Let's take a look at a more complicated example of static equilibrium. Here we have a 50-meter long diving board set up so that we have a support on one end of the board and a second support 20 meters from that same end. If the board has a mass of 60 kilograms, we want to find the amount of force exerted by each leg on the diving board. Okay, we're going to find FA and FB. Remember that the first step to solving these problems is to choose a coordinate system. Now, if you recall, when we talked about static equilibrium in the first video, we talked about this very figure where you have two different places where you can put the coordinate system. If you put the coordinate system on top of FA, everything will work out great. If you put it on top of FB, then you have torque, which exerts you have force A, which exerts a negative torque, and the weight of the board, which exerts a negative torque. It would be easier to do the first way. I'm going to do the second way just to show you a very, very important point here. So we're going to put our coordinate system right here. Maybe I should have had a different color. Let's go with a purple color. There we go. There's our coordinate system. Now you see, right away, we've got a problem. We didn't know where FA and FB were, so we're assuming that they are as pictured here in this figure. Each of these forces is going to exert a negative torque. So I could just flip FA around and then everything would be good. But I'm going to hold off on that. Let me show you why. All right. Remember our two conditions of equilibrium. The first is that the sum of forces is equal to 0. The second is that the sum of torques is equal to 0. Let's do the first one, the sum of forces. Okay, start off with this one. Well, what forces do we have? Force A, force B, and the weight of the board. All three of those forces are acting together. We need that sum to equal 0. Remember, F is equal to ma, but to be in static equilibrium, it needs to not be moving, so acceleration equals 0, therefore sum of F equals 0. Okay, well, this is good. I've got an equation, but I'm stuck here because I don't know FA or FB. So I need to move on to my, my torque equation. So here's our torque equation. The total torque has to equal 0. Now there are three forces in here, so I need to account for all three. Torque A, torque due to force A, torque due to force B, and torque due to the weight of the board. They all have to add up to 0. Now, I didn't add any signs on purpose. We already talked about how torque due to force A is going clockwise, so it's going to be negative. Torque due to the weight is also going clockwise, so it needs to be negative. What about the torque due to force B? What is the torque going to be due to force B? Well, how far is force B away from my center of rotation? Well, it's on the center of rotation, which means R for B is 0, which tells us that the torque due to B is equal to 0. So it doesn't matter what sign I put there, that's just going to be equal to 0. So that tells me then that the torque due to force A has to be negative torque due to the weight of the board. In other words, the torque due to force A has to be equal and opposite the torque from the mass of the board. All right, so now we need to do a side note here. Quick side note. What is RA? That's the distance from the center of rotation to force A, and that's just defined to be 20 meters. But what's RM? The distance from the center of rotation to where the force is applied. In other words, what's this distance right in here? Well, remember that the weight of the board is in the middle, which means that this whole width is 25 meters, but we know that this is 20. Therefore, what's left would be 5 meters. So the center of the RM, the distance from the pivot to the center of mass of the board, is 5 meters. Okay, let's use all that information now to solve for force A. Again, just so I remind myself, there's my center of rotation. That's the equation I just started with. And torque is equal to RF sine theta. So it's RF sine of 90 degrees in both cases. Why? Well, here's my R. Here's my F. Whoops, I didn't mean to do that. There's my R. There's my F. The angle between them is 90 degrees. So, and you'll find the same thing for the weight of the board. Sine of 90 degrees is just 1, so RAFA has to equal negative RM times mg. Solve for force A. That would be negative RM over RA times the weight of the board. So RM, we saw in the last figure, was 5 meters. RA is 20 meters. Mass of the board is given in the problem as 60 kilograms. And G is, of course, just 9.8. So pull out your calculator. And what do you get for force A? You get a negative 5 divided by 20. And then you have to multiply that, whatever that comes out to be, by 60 times 9.8. You get a solution of negative 147 newtons. Okay, what does this negative mean? It means that our direction for force A was in the wrong direction. So it's not like we see it there. Sorry, getting the right pen. Really, force A is going to be here. So force B pushes the board up, but force A holds that left end of the board down. That's really what we're saying is, and it worked out. So force A has a magnitude of 147 newtons in the downward direction. Okay, well that's force A. Well, what about force B? Well, remember back here, we did the sum of the forces equations in the top right over here. Well, we know FA now, so we can solve for FB using that same equation. So that was FA plus FB minus mg has to equal 0. So FB then has to equal mg minus FA, just solving for FB. And it was 60 kilograms times 9.8 meters per second squared minus FA, which I defined as, or which I found to be here as negative 147. I have to keep the negative in there because this equation, we were assuming FA is still upwards. So we have to keep that negative in there to keep the right, to correct the direction for FA. So then FB would be the weight of the board, 60 times 9.8, 588 newtons, plus 147 newtons, which gives us 147, 735 newtons. And from our previous slide, there you are. That is the value for both force A and force B.